Okay, so we're going to start doing our hand calculations. I have already gone through this most of the way and then realized I was on photo and not record because I'm using my phone for this. It was the best way to kind of set up this format. So we're going to be working through this. We'll play it up. I'm going to look how these videos look. Maybe we can find a better way. If somebody has a suggestion that's not going to cost me a fortune, let me know. So the first calculation we're going to do is the example for total force, or determining the resulting force. I always like to draw my examples of things. I just realized I have some multiple colored pens here. I know some people might be colorblind and it's less helpful, but for the rest of the class, it might be helpful to take a look at these. So I am going to redraw the problem here. Here's the axes they gave us, and we know that that's the x-axis and that's the y-axis. And they gave us 3 vectors. They gave us vector F1 equaled 10 meters. They gave us vector F2 equals 5 meters. And I'm gonna just start drawing the angles in here too. Ooh. And they gave us a third vector, F3 equals 7.5 meters. And they gave us this referenced from the x-axis. And then they provided us with what those angles were. Now, so the goal here is to add these vectors. Vectors don't add linearly. We know that there's a bit more to it than that. And the best way to do this is to break it down into its x and y components, because those do add linearly. If they're in the same line, we can add them very easily. So we'll break all of these down into their x and y components, add all of those up, and then we can use our right angle triangle rules and figure out what the hypotenuse is, or the resultant of those x and y components all summed up. So we'll do it in stages, and remember, you're going to have a question like this on the assignment that will be in stages. So you're going to need to take a deep breath, go through the calculations, check it out. You've got a week, take your time, do it a few times, and see if you get the answers that you like before you submit. So let's do vector 1. I always like to double check that all of these vectors are in the same units. And so we have M, M, and M, so meters for all of these. So we can go ahead and add these up. We have 10 meters for that vector. And we have our F1 y component and our F1 x component. I always like to stop and take a look, especially if I've drawn them roughly to scale, and predict which one I think is going to be bigger. And it looks like I should end up with F1x being the bigger value here. So let's take a look and start going through this. We know that if this is our angle right here of 22.5 degrees, we have an opposite, an adjacent, and a hypotenuse. Opposite is our F1y, adjacent is our F1x, and our hypotenuse is our 10. So if we want to know something about our opposite side, we know that that's the sine rule. Sine of our angle equals opposite over hypotenuse. And we know that if we want to know something about the adjacent side, it is cos equals adjacent over hypotenuse. So now we know the angle, we can solve what these are. F1y equals 10 times the sine of 35, 22.5, and F1x equals 10 times the cos of 22.5. We can solve these, and F1y equals 3.83 meters, and F1x equals 9.24 meters. F1x is bigger than F1y, which is what I predicted, so that works out nicely. Let's take a look at our F2. Now, I personally always like to work off the same axes. That way my sines and cosines are always the same. I'm always doing my y related to sine and my x related to cos or cosine. You don't have to do it that way. You can do it relative to the y-axis, but just remember opposite is slightly different. Opposite and adjacent are slightly different. In the slides, you see it done both ways. You can do it the way you like. I'm going to do it the way I consistently like to do it. So F2, which is my hypotenuse, is 5 meters. And I need to know my F2y component and my F2x component. Now, the angle they gave us was relative to here. They told us that was 22.5 degrees. For this to be the opposite side, I want to know what that angle is. So I can just figure that out. I know this whole thing is a right angle, so 90 minus 22.5, I'm going to get 67.5 degrees. Now I know that my F2y equals F2 times the sine of my angle, and F2x equals F2 times the cos of my angle. I have those pieces of information, so I can plug in 5 times the sine of 67.5 and 5 times the cosine of 67.5 degrees. And I can solve for F2 being 4.62 meters, and F2, so that was F2y, and F2x is 1.91 meters. I predicted that F2y would be bigger, and that seems to follow out with what I was talking about. All right. Well, that was a pain that I switched up the colors, wasn't it? Sorry about that. All right. F3. F3 our hypotenuse is 7.5 meters. And we have F3y and F3x. And we've been given this angle is 45 degrees. If I look at this, it's hard to see which one's going to be bigger. I didn't draw it perfectly to scale, but it's hard to tell. It's not obvious which one's going to be bigger. Some of you might already know exactly how they relate to each other, but let's just keep going through the calculation. My angle is referenced to the x-axis. It's going in a different direction than the other ones, so maybe that's something we'll need to think about, but we can come back to that. I also just realized that my nails look disgusting. It's because in class, my son is making Play-Doh, so last night at midnight, I had to do a trial run, and the food coloring stained absolutely everything on me. So, don't mind my disgusting fingernails. Next time I do calculations, hopefully I'll clean them up a little. Maybe I'll get a manicure. No, I won't. I'm too lazy. Okay, so we know what F3 is. We know what our angle relative to the x-axis is. We know that our F3y is F3 times the sine of our angle. And we know that F3x is F3 times the cos of our angle. We know those values. 7.5 times sine 45 degrees and 7.5 times cos 45 degrees. We can calculate that out and we get 5.3 meters and 5.3 meters. 45 degrees is halfway through 90 degrees. It makes sense that these should be equal to each other. Okay, so now we've broken everything down into its x and y components. Let's just note we actually did that one in red and that one in blue, just because I've made it somewhat confusing there. If we wanted, we could draw the tip to tail of all the x's and y's. I'm gonna try to do that here just a little bit. We had this as 5.3, our F2x, let's sum up our x's here. So let's sum up our x's. Our F2x was relatively short, and our F1x was quite long. So we have something funny here that if we actually drew this over top of this, remember it's tip to tail. This isn't tip to tail, this one's tail to tail. So we'd need to redraw this right here, and our resultant would be something like that. And the way we handle that is we say the sum of the forces in the x, so this little symbol means sum, the sum of the forces in the x, and everything going in this direction, that direction is positive, and everything going in that direction is negative. We're saying that we have minus 5.3, because that one's going in that direction, plus 1.91, plus 9.24. We sum all of that up, and we get that the sum of the forces in the x direction is 5.85 meters. Let's do the same thing for our y's. All of these are going in the upward direction. We have our, it's just gonna take up so much space on the paper. Well, they're all going in the same direction. I'm not gonna draw this one simply because it's gonna take up so much space. Let's sum all of the forces in the x direction. Upwards is gonna be positive, downwards would be negative. So going upwards, we have our F3x, which is 5.3. We have our F2y going upwards, which is 4.62. And we have our F1y, which is 3.83. If we add all of those up, we get 13.75 meters. So we're starting to get there. Now we have something that is our fx equals 5.85 and our fy equals 13.75. But what we want to know is the sum of all of the forces. We want that one big capital F. We want to know how big that is, and we also want to know what that angle is relative to the x-axis. Well, we know that if we have two sides of a triangle and an angle or a right angle in there, we know that F equals the square root of fx squared plus fy squared. So the square root of 5.85 squared plus 13.75 squared. And we can plug that all in into our calculator, and we get 14.94 meters. The last thing we want to know is this angle. And so this angle is relative to the x-axis. I just find that easiest to keep always talking about things relative to the x-axis. You don't have to, but you're going to find I'm always going to ask it relative to the x-axis. So pay attention. I'm going to tell you that that's what I'm going to do, but pay attention. I will be clear to put that in the question where it is applicable. As we move along, I'm not going to ask it that way because it should be obvious that that's what we're doing, or the answer is just what the total answer is. So now we want to know what the angle is. Well, if this is our angle, that's our opposite, and that's our adjacent. We know that the tangent of the angle equals opposite over adjacent. So the only thing we're missing here is the angle. So the angle is going to equal the inverse of the tangent of fy divided by fx. We can plug that into our calculator. I can actually plug that here in mine. So I'm going to do the second function tangent of fy, which was 13.75 divided by my fx. And we get that our angle is 66.95 degrees. And look, when we drew this, this is probably about the 45 degree. That seems right that we're just past our 45 degree. So that's our example one. I think this method worked pretty well. I'll go on and I might do these equations step by step.